Okay, good evening, everyone. So can you hear me now?
Sir,
Okay, hi. So welcome to today's lecture. So how was the exam? How was the midterm exam? Anybody from the students?
sir, it was good. We were able to answer all the questions and also within time.
Okay, good. So I think the question paper was doable in 1 hour. Okay, and then I think the questions are also straightforward. Okay, so I think that is good to know. Any other feedback, anybody, or that is okay with everyone?
Yes, sir. Everybody able to answer it, sir.
Okay, good. All right. So let's begin today's lecture. So all right. So there is one thing that I want to say before moving forward. So I mean, for the midterm exam, you have brought your own answer sheet, right? I mean, your own formula sheet, right? So for the final exam, there is a small change. For the final exam, I mean, of course, you are welcome to carry a formula sheet, but then I mean, you will not carry the formula sheet. You are allowed to you are allowed a formula sheet. But what we do is that I'll ask you to give me whatever 1 page or 2 page formula sheet. Okay, so that means all of you have to collaborate and then type up or write whatever, and then give me a 2 page formula sheet so that I can put that together with the question paper and give it to you. Okay, because the way the exam will be conducted, it is difficult if you bring your own sheet with you. So that's the reason. So what I wanted to do is that you give me sufficiently in advance. Maybe I'll tell you a date. Um, Okay, so by then you should give me a 2 page formula sheet in which you write whatever you want to carry. But then this is where all of you have to kind of collaborate. Okay, so share a Word document or something among yourself and then start writing all these equations that you want to use in the final exam, and then give it to me so that I will include it with the question paper. Okay, is that all right with everybody?
Okay, sir.
Okay. Um, okay. All right. So let's get started. So we will look at the so far we have been looking at solution to first order ordinary differential equations, right? So we have been looking at this dy by dt equals f of t comma y, and we saw how this can be integrated with several methods. We looked at the Euler method, whether it is explicit or implicit. We looked at the trapezoidal method. We have also looked at Taylor series method. Okay, and then we have also looked at the special methods, which are known as the Runge-Kutta methods. We looked at the RK2 and RK4. The RK methods are special in a sense that these methods do not require, unlike the Taylor series method, they do not require the function derivatives to be evaluated to obtain a higher order accurate result. Rather, you will do more function evaluations at intermediate points between n and n plus 1, and then you're going to obtain a higher order accuracy, such as globally second order accurate and globally fourth order accurate, depending on which method we're going to use. Okay, so that is what we have learned so far. Now we're going to look at now. There are, of course, also there are some multi-step methods and so on, which we are not going to look at. But let us move on to solution to system of first order ordinary differential equations. Okay, so that means we're going to look at a set of ordinary differential equations system, and each of them is a first order ODE. Okay, so when do we get these kind of system of first order ODEs? Well, of course, if you have to solve a higher order ODE, we said that a higher order ODE can be transformed to system of first order ODEs. Okay, that is one application where you're going to get system of first order ODEs, and otherwise system of first order ODEs also naturally occur in certain cases, such as chemical reaction of species, or in vibration of a complex system with several elements, and so on. Okay, so these kind of also naturally occur. System of first order ODEs also occur in vibration of a complex system or in chemical reaction of species, and so on. Okay, so then how do we represent, how do we write this equation? So if it was first order, if it is a single equation, we have written it something like this. Now we are dealing with a system, so let me write this as so we have written earlier y prime equals f of t comma y. So this is a single equation. Okay, now I want to write y bar prime equals f bar of t comma y bar. Okay, now what does this mean? Here bar indicates that this is a vector quantity, so bar indicates that this is a vector quantity. That means y bar is basically nothing but we have y1, y2, y3 all the way to ym. Okay, so we have a vector that is y1 to ym. Okay, so that is, there are so many variables y, and then y prime bar is again going to be y1 bar prime, y2 prime, and so on, right? So that means the primes are basically derivatives of each of these values, and then this function f bar, we have f bar is a vector function. Okay, so it is a vector function in which the way we can write it is f bar equals fi of y1, y2, y3 all the way to ym comma t, and I goes from 1, 2, 3 all the way to m. That means we have m functions. Each function is could be a function of y1 to ym comma t. Okay, so that is what we have, and then this is the system of equations that we have to solve to obtain a solution, and that solution is basically we want to obtain how does y1 vary with time, y2 vary with time, and so on, and then ym varies with time. So essentially we want to obtain this solution of y1 to ym as a function of time. Okay, that is the idea. Okay, so if this is the case, now how do we go about solving this? Now from an application point of view, there is no difference between solving a single equation and solving a system of equations. Okay, that means we can it is straightforward to apply, let us say, the explicit Euler method to system of ordinary differential equations, just like the way we have applied explicit Euler method to a single ODE. Okay, that means what we can write is, so in the context of a single ODE, we have written, if we have y prime equals f of t comma y, we have written explicit Euler as yn plus 1 equals yn plus f of, I think we wrote as a subscript probably, yn plus 1 equals yn plus h times f of tn comma yn, right? That is what we have written. Similarly, for this y bar prime equals f bar of t comma y bar, we can apply explicit Euler method. That is going to be y bar n plus 1 equals y bar n plus h times f bar of t comma y bar n. Okay, that is what we can write, where h again is the step size. Okay, so that is the step size as in the case of explicit Euler method. So it is kind of, there is not much difference. That means if I were to write slightly differently, instead of using bar, if I were to write using I, where I is varying from 1 to m, then I can write this yn, okay, yi. I'm writing n plus 1 on the numerator, but n plus 1 in the numerator doesn't denote yi is raised to the power n plus 1. It just denotes that yi at n plus 1's time level equals yi at n plus lambda times fi function of tn comma tn comma y I at n. Okay, so I can also write tn. Okay, it just means that it is basically at this thing. So this is where I goes from 1, 2, 3 all the way to m. Okay, so that is your explicit Euler method. Okay. However, conceptually, there is a difference between solving for a single ODE and solving for a system of ODEs. And what is that difference? That difference is the stiffness problem. Okay, that difference is known as the stiffness problem, which doesn't exist in a single ODE, but only occurs in solution of system of ODEs. Okay, so that is the stiffness problem. What does stiffness problem mean? When we have a system that is composed of several responses, okay, if the rates of response of the system vary or a range of orders of magnitude, that means for a system composed of a range of responses and the system needs to be integrated to a very long time, then we encounter the stiffness problem. Okay, that means the stiffness problem can be encountered in chemical reactions when the reaction rates are very different. That means, let us say one reaction happens over a few milliseconds, another reaction happens over a few seconds, then there is a very large range of reaction rates. The time scales are very different, then the stiffness problem can occur. Similarly, when you have, let us say, if you have a complex system, let's say with multiple springs or even two springs, one of which is very stiff and the other is very flexible. Okay. In such situation also, you can encounter stiffness problem. Okay. So we will look into what stiffness problem is in detail a little more as we get into the lecture. Okay. Before we do that, let us identify a model problem. Okay. Just like we have done a model problem. So let us identify a model problem for solving system of ordinary differential equations. Okay. So the model problem we have chosen for a single equation was y prime equals lambda times y. Okay. That is the model problem we have chosen for the single equation. Similarly, I want to choose y bar prime equals a times y bar as the model problem. Okay, for solving system of ordinary differential equations. Okay, and now where A is basically an m by m matrix, and it has constant values, but the entries could be complex. Okay, they can be complex just like the way the lambda was complex in the case of a single ODE. Okay, that means we have this matrix A in which is an m by m matrix where each of the entry could be a complex number, but there are m by m entries is what we have. Okay, so we kind of say that this is the model problem that we want to work with, which is in line with the model problem that we have chosen for the single ODE. Okay, so and we have also said in the case of a single ODE that if lambda r is less than or equal to 0, then we obtain physically relevant and possible solutions, right? That's what we have said. Okay. Now, what would be the corresponding condition for the system of ODEs? Okay, where we have said y prime equals a times y bar. Okay, y prime equals a times y bar prime equals a times y bar. What would be the corresponding condition, something like this, that we have to satisfy? It turns out from linear algebra, if the eigenvalues of matrix A have negative real parts, then the solution is bounded. Okay, so the corresponding condition in the context of system of ODEs is that the eigenvalues of A should have negative real, the real values, the real part should have negative values for the real part, and then we know that the solution actually converges or it is kind of remains bounded. If it doesn't, then the solution is going to be unbounded, which we are not interested in. We are not going to get such a problem in reality. Okay, so that is the idea here. Now, if this is the case, we can write down what would be the explicit Euler method version of the of the model problem. So let us write down for the model problem or the explicit Euler method for the model problem. Okay, that means we have written y I n plus 1 equals y I n plus h times f of fi of t comma y I n, right? That is what we have written, and then we have y bar prime equals a times y bar. Okay, so this is the model problem. So let us apply the explicit Euler method to this to solve this model problem. That means we're going to get basically y bar n plus 1 equals y bar n plus h times a times y bar n, right? So essentially I apply this model problem to this explicit Euler method or the other way around. Okay, I'm going to apply explicit Euler method to this model problem, and then I'm going to basically get this equation, right? I'm going to get this equation, which is here, which is y bar n plus 1 equals y bar n plus h times a times y bar n. Again, we realize that here n plus 1 is basically the value at time level n and n plus 1. Okay, fine. Okay, that means I can also write this as, because this is y bar n and this is a matrix, I can write this as matrix I plus h times a times y bar n. Okay, that is going to be y bar n plus 1, where this is the identity matrix. Okay, because I have taken y bar n out. Then we can also write this as y bar n equals I plus ha to the power n times y bar 0, right? Just like the way we have done before, I will basically get a factor of I plus ha with each n to n plus 1, right? From 1 to 2, 2 to 3, and so on. So as a result, y bar at n can be expressed in terms of y bar of 0 as I plus ha to the power n. Okay, that means we are saying that this is my new matrix. Okay, let us call this new matrix as B. P to the power n times y bar 0. If I were to multiply, I'm going to get y bar n. Okay, so now we are talking about how to solve this problem numerically, right? Using explicit Euler. That means using explicit Euler, we have y bar n equals B matrix raised to the power n times y bar 0. Okay, so that is what we want to solve. Okay, this is what we want to solve numerically. Now, now if this is the case, under what conditions will this b to the power n decay to 0, right? Essentially, what we said was, we said for stability in the case of us solving a single ODE, we said y n equals sigma n to the times y0, right? That's what we said. Where if the modulus of sigma is less than or equal to 1, then we said sigma n will decay to a very small value, and then yn becomes bounded, right? We will basically get a bounded solution for yn when sigma is less than or equal to 1, and then basically decays to 0 as sigma is raised to the power n. Okay, now what is the corresponding condition in the context of b to the power n? It, again, we are not basically trying to prove this thing again from linear algebra. We know that linear algebra basically tells us if we have a matrix C, if we raise it to the power n, in the limit of C being raised to the power n, it will decay to 0 only if all the eigenvalues only if the moduli of all the eigenvalues are less than 1. Okay, this is a similar condition as what we have identified here. Here we say that sigma, the amplification factor, should be less than or equal to 1, whereas in the context of having a matrix, we know that in the limit of c to the power n tends to 0, or limit n tends to infinity, c to the power n goes to 0, only if the moduli, that means the modulus that we take of all the eigenvalues are less than 1. Okay, if this is satisfied, then we know that we basically get a bounded solution. Y bar n will decay to some converged value. Okay, now what is the Cn? Okay, the Cn is basically nothing but b to the power n here. But then what would be the eigenvalues of the matrix I plus Ha? Okay, so we know that the matrix, let us say A, has eigenvalues. Let us say we are able to calculate the eigenvalues of matrix A. Okay, because we are prescribing that matrix, so we know what is that matrix on the right hand side. Let us say if the matrix A has eigenvalues lambda I, where I goes from 1, 2, 3 all the way to m, then the eigenvalues for the matrix I plus Ha, which we have used here, right, would be, again, from linear algebra. We know that these eigenvalues would be essentially 1 plus lambda I times h, right? Simply because the eigenvalues of identity matrix would be 1, and then the eigenvalues of these will be multiplied with h. So as a result, what you get is 1 plus lambda IH is what you're going to get. That means for all the eigenvalues, if they are less than or equal to 1, then we know that the B to the power M matrix will give bounded solution. Okay. So that is what we know from the linear algebra. Okay. That means what is 1 plus lambda I less than or equal to H for all I going from 1 to M, as I have written here. Okay. So basically that condition can basically now we have multiple conditions, right? Earlier we just had one condition where my lambda is lambda times H, 1 plus lambda times H is less than or equal to 1, right? That is what we had in the context of a single ODE. But then now we have 1 plus lambda IH is less than or equal to 1, where lambda I are different eigenvalues. You have M different eigenvalues, okay? But we know that the larger the eigenvalue, the smaller will be the value of H, right? That means the smallest H that we can take, right? Because from here we can only take the smallest H, because that is going to be the limit, of what H can we take is going to be the smallest H. That smallest H is dictated by the largest eigenvalue. That means from this condition, we know that the smallest H is dictated by the largest eigenvalue. That means H should be less than or equal to, if I were to write this, it's going to be 2 times divided by modulus of lambda maximum, right? Like the way we have done before, 2 times mod lambda. But then now the largest eigenvalue is going to tell you what is the smallest H you can take, and we must take that H so that we can integrate. That means if we have a system, we would take this H value and then use that H value when we have written all these formulae, right? So essentially here, what H should I take? This H is basically dictated by 2 by modulus of lambda max. Okay, so basically if I assume that this has, this is again assuming that the all the eigenvalues are real and negative, right? So essentially this is the condition we would get, right? Because essentially we are again on the real axis, right? If all the eigenvalues are real and negative, then this is the condition I would get for H. Okay, now I think it is easy to see what we meant by the stiffness problem. Okay, so as you can see, although we have, if let us say, if the matrix A has eigenvalues lambda 1, lambda 2, lambda 3, and so on to lambda m, out of this we're going to obtain what is the maximum eigenvalue and then the minimum eigenvalue, right? We can obtain that. If these two are much farther apart, that means the ratio of the maximum eigenvalue to the minimum eigenvalue is much greater than 1. That means one of them is of the order of thousands, the other one could be order of, let us say, very small, or even one of them could be order of, let us say, 1e minus 3, the other one is of the order of 1e minus 6. Okay, if this is the case, then we have modulus of lambda max by modulus lambda min much greater than 1. In this case, and if we need to integrate the equations to a long time, if we need to integrate the equations to a long time, that means the solution is required over a very long time, then we have what is known as the stiffness problem. Okay, because this lambda max, modulus of lambda max, is dictated by the, as we said, is dictated by the fastest response, right? This dictated by the fastest response of the system. Okay, whereas lambda min is dictated by the slowest, okay, slowly varying or slowly varying solution. This is the slow. That means when we have a very stiff spring and when we have a very flexible spring, then you can get these kind of things. Also in chemical reactions where some chemicals are reacting very quickly, and then others are reacting very slowly. Okay, now why is that a problem? That means when this is very large, when this ratio is very large, then our delta T, which is dictated using H, becomes very small, right? That means, although, let us say, but then if we are interested in a very long time behavior, where things are changing very slowly, right? Because lambda max is the fastest response time. That means when things have happened from t equal to 0, the fastest response solution has already responded, and then you're only left with the slowly responding part of the solution, right? This has already responded, and then the slowly varying response is still changing. However, what we see is that we cannot still take h coming from this lambda min, which could have been h max equals 2 by modulus of lambda min. Rather, we still have to take h min, which was coming from 2 by lambda max, although we have now crossed the time where the fastest response a part of the solution is already crossed. Even then, we are still limited by taking the small delta t to integrate. Okay, so that is the stiffness problem, right? That means you have a very long time that you have to integrate, but then you can only take a very small delta t, which is dictated by your lambda max. Although it is not the part of the solution that is still evolving, right? Although the part of the solution that is still evolving is the slowest part, the fastest one has already might have responded, but then the solution is still changing slowly with respect to time. But then you are still limited by the h max, by the h min, which is basically dictated by lambda max. Okay, and now this is a problem for the explicit methods. Okay, because if we do not take the h to be minimum, then what will happen is that the solution will diverge. Although the fastest response thing is not playing a role here, it is still part of the solution. It is a very it is still, because the round of errors associated with the fastest response will grow and make the solution unbounded. Okay, so that is the reason.
Sir, one thing I want to ask you is this:
Yeah.
lambda max by lambda min, the modulus of that, is that
Yeah.
related to the concept that you have taught us during the norm of the vector, norm of the matrix?
Norm you can take, but then this is basically just a modulus.
Yeah, but the ratio that you have defined in the beginning, sir, actually, so lambda max and lambda
I
min
see.
should
Yeah,
be 10
it's somewhat
zero.
related. Yes. So essentially, we said this thing related to. We said when you have there, what we said
Ill
was
conditions and good condition in that way, right, sir?
correct. So we said this is basically will lead to ill-posed problems, right? So we talked about the condition number.
Right, K2A.
Yeah. So this is exactly connected again. So this is again condition number. You can think of it in that sense. That means if your condition number of the matrix is very large, then you are required to integrate over a very long time, then that is what we call it as a very stiff problem. Okay. Or if your condition number is not so large, then you can only integrate with whatever delta t that is possible, right? That is not an issue at that time. So yes, this is related to the condition number, right? If the condition number of the matrix is very large and the solution is desired over a very long period of time of integration, then we call this as a stiff problem. Okay, because otherwise we would have taken a very large delta t and then obtained the solution very quickly. But we are unfortunately unable to do that. We still have to take very small delta t and then integrate to a very large t, right? Let us say this time is in the terms of 10 to the 6, and we still have to take some 0.001 or something, and then still we have to do 10 power 6 divided by 0.001, which is basically 10 to the 9 steps we have to do. If this was not the case, if the condition number was small, then we would have taken whatever is the h that is required, which is basically there is no stiffness associated with it. Okay. Yes, thank you. I think that is a good connection you have made. Okay. So where do we see these problems, this kind of stiffness issues? As I said, we will see that in chemical reactions. very often. And then we also see that in systems with springs. Okay, or we also see it in fluid mechanics in the context of boundary layers. In the context of boundary layers, where there are two regions. One is the viscous region and then the outer region. Okay, so these two basically introduce two different length scales, one delta and then one outer length scale L, which basically cause some kind of a stiffness problem. Okay, so that is the idea. So what is the one easy way to avoid stiffness problem is to use implicit methods. Implicit methods come handy in the solution of stiff problems. Okay, in the solution of stiff problems, because when you use implicit methods, as you know, there is no problem in terms of stability, right? Because implicit methods are usually unconditionally stable. Okay, implicit methods are usually unconditionally stable. As a result, there is no problem with stability. But as far as the accuracy is concerned, we have to use that wisely. So what we will do is that when you use implicit methods, we will take a small time step, either h or delta t, in the solution or in the quickly varying part of the solution. Okay. However, we can take larger delta t, larger h or delta t in the slowly varying part of the solution. Okay, such that we will still be able to solve the problem in a meaningful amount of time by taking larger delta t. And we know that because it is an implicit method, there is no conditional stability, so the round of errors are not going to grow. Okay, that means, let us say if I obtain a solution, let us say something like this. If my solution is, let us say, varying slowly with respect to time, then I can take actually larger delta t, right? But then let us say after some time we know that the quickly varying part kicks in which the solution is varying much more quickly like this, right, while it is still growing. Then we know that we have to take a very small delta t in this region. Okay, so that means we can still solve this problem with in the minimum number of steps. Minimum number of steps by adaptively taking the time step to be very small or very large, depending on how the solution is varying within the problem. So we need to get some idea about how the solution varies, because we don't know that a priori. Okay, only then we will be able to use wisely. So there are many methods that are available for solving stiff ODEs. Even MATLAB has a stiff ODE solvers. That is ODE 23S is a stiff ODE solver. Similarly, LSODE, the linear stiff ODE solver, and so on, which can be used for solving this thing. And there are many other separately developed methods other than just the implicit methods. Okay, there are other methods available for solving stiff ODEs, which we are not going to go into too much detail. But this is an active area of research. Solving for stiff ODEs, which essentially come up in many physical situations. Okay, fine. So, but then we realize that any questions so far? Have you come across any stiff ODEs in your work so far? When you're dealing with, let us say, automobiles or FEA analysis or fluid mechanics?
Sir, my understanding is, okay, there is some situation like where in in CFD or something like if there is a long pipe is there and if we need to bring it to very short, like assuming that longer tube needs to be converted into a smaller one, very small one. I believe maybe in that region, maybe we can apply that this one.
Okay. Not really. So what you're saying is in terms of changing the dimension of the problem. But what we're talking about is dimension of the problem is fixed. But then the way the system responds is very different for a range of time, and then it is very different for another range of time. Maybe so. Let us say if you have some system that is mounted on some kind of a damper mechanism or something like that. Okay, and then again you use, let us say, very highly viscous fluid in one of them. Okay, in the other one is basically very low viscous fluid, right? So the damping that is offered by the low viscous fluid is very small. So as a result, the oscillations are sustained over a period of time, whereas the highly viscous fluid is going to damp it very quickly, right? So the oscillations are gone. But then when these two are combined, what you have is that the system responds in a slightly different way. Okay. For example, these high frequency dampings are eventually damped, but then which will be taken over by this one. Okay. So in that context, you have built in two different scales, right? Not just one, two different scales, and each of them responds at different rates. And then when you want to integrate for a very long time, then you have this problem, right? That you cannot, if you use explicit methods, you cannot go with a larger delta T, although your system is varying slowly. Okay, that is the idea. I can't think of a better physical explanation. Maybe if you come across something, you let me know. Yeah.
Sure, sir. Thank you.
Yeah. Okay. Fine. So let me then. Okay, but then we know that one interesting thing about implicit methods is that implicit methods, let us say, especially if there are non-linearities, non-linear f function of t comma y, f bar t comma y bar, then we need to use methods like Newton-Raphson, right? Methods like Newton-Raphson, or iterative methods, other iterative methods to solve for the solution, right? So this is kind of one downside that we have noted before. But then what we have said was, for implicit methods, if you have only a single equation, we said we can basically linearize the non-linearities, right? And we can solve for the solution of this linearized system rather than the non-linear system, and then the linear system can be integrated to obtain the final solution. We have seen this both in the context of implicit Euler as well as in the context of the trapezoidal method. Okay, so in both of this context, we have seen that it is possible to linearize. It turns out it is also possible to linearize the system of equations. Linearize system of ODEs, just like the way we have linearized the single equation. Okay, so to do that, I'm going to consider again your equation. Your equation was we have considered earlier dy bar by dt equals f of t comma y bar. So I'm going to slightly change this, and then I'm going to consider du bar by dt equals f of t comma u bar. Okay, so that's what I'm going to consider. Then if I were to apply an implicit method, let us say I will apply trapezoidal method to solve this equation, then my solution is basically going to be u bar n plus 1 equals u bar n plus we have h by 2 times f of t comma tn comma u bar n plus we have f bar of tn plus 1 comma u bar n plus 1, right? That is the trapezoidal method that we have learned. Only thing is that only difference is earlier we had u, now we have u bar, right? So that is the only difference, because now we are applying to a system of equations. Okay, you can compare. Okay, so that's what we are applying. But then we said the main problem is with this term. This is basically the nonlinear term, right? F bar itself is nonlinear, and then if you want to calculate f bar at t bar n plus 1, u bar n plus 1, u bar itself is unknown. But then u bar n plus 1, if it occurs as u bar n plus 1 times u bar n plus 1, then we cannot really solve for it, right? So that is the problem. But then, of course, we can use Taylor series expansion. And linearize. So how are we going to linearize? We're going to say f bar of t n plus 1, u bar n plus 1. We're going to linearize about f bar of t n plus 1, u bar n. Remember, we don't have to, we already know t n plus 1. Only thing we don't know is u bar n plus 1. So as a result, we are only normalizing with respect to u bar n rather than tn, okay? Because tn plus 1 is already known. We know the time, right? Tn plus delta t is tn plus 1. So we know that, okay? Then plus, because I'm normalizing with respect, because I'm expanding about u bar n, I need to consider differences between u bar n and u bar n plus 1, okay? So instead of writing u bar, I'm going to write uj n plus 1 minus uj n. That is going to be, that is like your xi plus 1 minus xi times dou f by dou x, right? Dou f by dou x. Instead of that, I'm writing dou f, okay? So let me write it for, instead of bar, let me write it for each I, okay? So this is fi, this is fi. So dou fi divided by dou uj, right? That is what I have, because this is going to be xn plus 1 minus xn divided by dou f by dou x, right? So that is what we have written. Of course, there are m such elements, so that means I'm going to get m such values, which all need to be summed. So j goes from 1 to m, plus we have a second order accurate terms here, which are going to be order x square, which I'm not writing, okay? Of course, now this equation is what we have obtained. This is the Taylor series expansion. So instead of writing dou f by dou x1, dou f by dou x2, and so on, times x1 n plus 1 minus x1 and x2 n plus 1 minus x2 and so on, we have written in a summation in a compact way like this. Now this can also be written in terms of a matrix form, where we can write f bar t n plus 1, u bar n plus 1 equals f bar t n plus 1, u bar n, plus this matrix dou f by dou j can be written as some matrix a sub n times what I have is this u bar n plus 1 minus u bar n. Okay, that is the vector. Okay, what is the matrix an? An is the Jacobian matrix. An is the Jacobian matrix, which is nothing but, which has entries dou fi by dou uj. That means an can be written as dou f1 by dou u1, dou f1 by dou u2, all the way dou f1 by dou um. Then we have dou f2 by dou u2, dou f2 by dou u2, and the one dou f2 by dou um. Okay, similarly we have dou fm by partial u1, partial fm by partial f2, partial fm by partial um. Okay, so that is the n by m matrix. That means once we know the functional form on the right hand side, which is this f of t comma u bar, f of t comma, I mean, I know what is f1, f2, and so on, fi, u1, u2, all the way to um. I can definitely calculate what is the partial f by partial u1, partial f by partial u2, and so on. Okay, so those are the entries that we have used here. Okay, that means we can calculate how does the right hand side function f change with respect to u1, u2, u3, and then form this Jacobian matrix. Once we have the Jacobian matrix, we can simply multiply with uin plus 1 and uin to form this thing. Now what we need to do is that we have linearized this. We have linearized the this function. So we're going to basically go and substitute in this one. That is going to be u bar n plus 1. So I'm going to just rewrite this thing. So what we have is u bar n plus 1 equals u bar n plus h by 2 times f of t comma u bar n plus f of Tn plus 1 comma u bar n plus 1. And then we're going to substitute for the linearized part of this thing. That's going to be u bar n plus 1 equals u bar n plus h by 2 times f of Tn u bar n plus this linearized part is f of Tn plus 1 u bar n. And then we have plus, what did we get? We got an, okay, times u bar n plus 1 minus u bar n. Okay, that is what we got. Okay, so if I were to send u bar n plus 1 with its multiplication factor an and h by 2 to left hand side and retain the coefficient of u bar n on the left hand side and merge with this thing, then we have u bar n plus 1 times, you're going to get an matrix I, and then this h by 2 times an is going to, when you go left hand side, you get minus h by 2 an equals on the right hand side also we get u bar n. You have I coming from here, this is 1, and then you have minus an times h by 2 minus an. An might be easy if I write it inside. Okay, so we have an, and then I have plus h by 2 times f of Tn u bar n plus f of Tn plus 1 un. Okay, so this is what we have. That means we have to solve for this system, or I think we should write it as on the right hand side instead of here, because we are writing it as column vectors. Okay, equals I times un. That is better. Okay, so this matrix times this column vector equals this thing. So we have now system of equations in the form of ax equal to b. Okay, this is not exactly ax equal to b. This is ax equals some a u a n bar times this thing. Okay, so but this can be solved, right? You can use Gaussian elimination or something and then solve for this one. Okay, or even probably it is maybe even simpler. Oh no, it may not be, because an is going to be Jacobian matrix, which is full matrix, so we have to use some kind of Gaussian elimination, calculate ui bar n plus 1. Okay, once you know ui bar n plus 1, then you can go to the next level, u bar n plus 2 and so on. Okay, so that is how we can solve it. But then one thing to note here is that an matrix is not a constant matrix, right? Because an matrix is composed of partial fi by partial uj. This is not constant. That means as we solve, we need to update or recompute an from time to time. Okay, while using this method. Okay, if it so comes out that dou fi by dou uj is independent of time, then you don't have a problem, right? But that is not going to be in general the case. So an is not a constant matrix, so a has to be updated from time to time. That means as you iterate, an has to be recomputed. So you have to go back and keep calculating what is dou fi by dou uj for every time. It could be a function of time, and then that particular time needs to be updated. I mean, we are evaluating, where are we evaluating this matrix an? We are evaluating this at Tn plus 1 u bar n, right? That is where we are evaluating this entire matrix, isn't it? Because this is expanded about Tn plus 1 u bar n. Okay, so that is what we would do. Okay, we are out of time, so I'm going to stop here, guys, unless you have any questions. Otherwise, we're going to meet tomorrow and then look at, so that finishes the.
Sir, I have some questions, sir. Can I print my screen, sir, if you allow, please?
Yeah, please go ahead. Yeah, go ahead.
Yes, sir. So I'm sharing my screen, sir.
Oh, you want to share a screen? Okay, fine.
Yes, sir. So is that visible to you, sir, please?
Yes, yeah.
So this is regarding the assignment number 2, question number 2.
Mm-hmm.
So here, the function that can be written in two ways. That is basically 100 minus this whole thing coming to one side. And And second option that has been like shared by you is that let us solve this, simplify this, and then take the derivative.
Hmm.
So in my opinion, sir, when I'm what I've done is I've taken this left side and try to differentiate it. So
Hmm.
differentiation of that function and differentiation of this function will be completely different in that way. So like what I mean to say is ki, if I simplify this this function and then take the derivative, it is changing the nature of the function in my opinion.
Correct,
So
correct. It will
what is the
change.
right
It will
way, sir?
change. Yeah.
What is the right way, sir? Like, should we take this
Uh,
completely by this side and solve?
There is no right. So is it actually changing the convergence path of the problem also?
My answer that I have got is around 14 point something, and
Ah.
like Vivekanand has solved like this, so he's getting around 3.95, which is the
I see.
mention
Okay,
over here.
okay. Okay,
So-
just 1 second.
Yeah.
Yeah.
So because imagine, sir, suppose x square plus 5 divided by x is equal to 4. If I solve it, then I will get only 2x plus some constant. But if I take x square plus 9 divided by x minus 4 is equal to 0, fx, and then solve it, then I will get denominator x square. So the complete nature of the function is changing actually in that way. So which is the right
Yeah.
approach to be taken up?
There is no right approach to that. I mean, both of them ideally should converge to see. The thing is that in one of them, the Newton's method is not converging properly, right?
Okay.
You are ending up with a problem where either it is, shooting to some solution which is not there or something like that. That
sir,
is, yeah.
So actually what we see is in both methods, the final convergence is the same value, but on the fifth iteration, the values are different.
Oh, I see. Okay. If it is converging to the same value, then there is no problem. See, otherwise what is happening is if they're converging to the same value, then it's okay. The nature of equation can change because
So
you are
probably this will take lesser step to get
is-
resolved, and this
Yes.
approach will take more step to get to the final value. That could be the case,
Possible.
right, sir?
Yes, that is possible. But unfortunately, you will not know unless you do different methods, which one will take lesser or which one will take more. That is the issue. So you basically, but then it may so happen that if you rearrange the problem, if you rearrange the function, it may look different, and Newton iteration may not even converge for one particular problem. That is also possible, right? So this is basically exactly equal to it's exactly same as what we have done. We have looked at what are the limitations of Newton's method, right? We said if there is the function is such that it can go into an infinite iterations, between two x1 and x2, right? It can go and keep in infinite iterations, or it can even shoot into infinity, right? If you have the derivative going to 0. So if you rearrange the function, it may be possible that the derivatives are very small, in which case it can go to infinity values. That is possible. But then again, if you rearrange it, it may be possible that one method doesn't even converge. That is there. But there is no right or wrong way of doing this. Basically, you can always rearrange this function into whatever form and then try to work with that. It may be easier to calculate derivatives in one way than the other, but if it converges to the same answer, then I think it is okay.
Okay, sir. Got it, sir.
Yeah.
Thank you.
Yeah, but the number of iterations can be very, very much different. That is possible.
Okay, sir. And second problem is second query that I have, sir, is regarding the assignment number 3, problem number 1. So you have asked us to calculate like second order derivative to the fourth order accuracy in that way.
Correct. Yeah.
So by the definition that the concept that you have taught in the class, sir. So basically R is equal to 2 and M is equal to 4. So total stencil size is basically 4 plus 2 is equal to 6, right, sir?
Yeah.
So we have to expand this I plus 1, I plus 2, I plus 3, I plus 4, I plus 5 in that way.
But because of symmetry, it might reduce to n plus r minus 1, isn't it?
Oh,
no, so this is forward. This thing.
Oh, this is only forward difference. Okay, not symmetry. Okay. This is not central. This is only forward, is it? Then you would need all the 5 points. Yeah.
So basically, sir, we have tried to solve it, and then what we have done is that since order 5, when divided by h, will become order 4 accurate. So we need now to expand the fifth order completely, right, sir? Taylor series. Up to fourth order we can expand, and then alpha plus beta, alpha, beta, and gamma, and suppose delta. We just take a unknown of that coefficient and solve the matrix by Gaussian elimination, or get the value of alpha, beta, and gamma, and delta, and this. So that should be okay, na, sir?
Yeah, I mean, essentially, you should get fourth order. I mean, the truncation error should be order delta h power 4.
Okay, sir.
Yeah. So
Okay, sir.
this is del square u by del x square to fourth order accuracy using one-sided differencing. Is it like using forward
Right. So
differential?
forward difference method. Actually.
Forward difference formula. Okay. I think then what you're saying is correct.
Noted, sir. Thank you so much.
You'll get the basically a matrix and then use Gaussian elimination to find the solution. Yeah.
Sir, one doubt here, sir, regarding this Gaussian elimination. What I tried was I was trying partial pivoting for the Gaussian elimination, and when I did Gaussian and partial pivoting, the values were coming implausible, whereas only doing Gaussian elimination was giving plausible values. Then when I was looking into the literature, it was saying that when we have a large partial pivoting row, then this may not give a plausible value. So is there some scenario where we should not use partial pivoting, sir, based on the
No,
matrix,
should not be the case actually. Partial pivoting should work. I mean, whenever that is kind of surprising because if it is working without pivoting, it should work without partial pivoting also. I mean, partial pivoting should also give you correct answer, just like the way you do. I don't see why it is. Because you are only trying to reduce your round of errors, by bringing the largest element to the pivot position.
Okay, sir. Maybe I'll check. Maybe I made some numerical mistake.
Yeah, you can check again because if it is already working without pivoting, it should work with partial pivoting also. Yeah.
Okay. So, can we solve this MATLAB? I mean, Gaussian elimination using MATLAB, or should we do it manually, sir, for the assignment?
You can do it. You can do it with MATLAB. That's okay. But then I want you to do it by hand so that you get practice.
Sure, sir. Sure. Okay.
See, so for example, let us say tomorrow, if this question comes in, exam or something, you have to do by hand only.
Okay, sir. Thank you.
Right. So that's the idea why I gave. But but then the programming part, wherever the programming part that is there, you can do it with MATLAB. Let us say in the programming part, I asked you to use this or some other method. Then you can quickly derive and then use whatever MATLAB to get the final answer, and then use that scheme for the solution.
Okay.
So my screen is visible to you, sir. If I'm not wrong, right?
Sorry, say it again.
My screen is visible to you.
Yeah, it is still visible. Yes.
So basically, sir, this what we have tried is like UI, considering UI as a factor.
Correct.
Also.
Correct. Yeah.
1, 2, 3, 4, 5 like that.
Yeah.
So what I have done is, sir, I have excluded expanding this fifth order, because when I divide it by h, it will become fourth order, and ultimately we want fourth order accuracy, right, sir?
Correct. Yes.
So in that way, we have just tried to figure out what are the alpha, beta, and gamma value using this Gaussian elimination, and try to do like this. What is the value of like this?
Yeah.
I think
But why will you divide? Yeah, this looks good only. This looks fine. Why will you divide with only h, not with h square?
H square is coming, sir, because of this. What I mean to say, this factor is coming over here.
By
h square, actually.
Okay. It is h square only, no?
Yeah.
Okay. No, I got confused a little bit when you said when you divide with h.
No. What I mean to say, sir, like suppose if I put over here h to the power 5 divided by factorial 5 and try to expand that also, but you wanted order 4th, sir, accuracy.
Yeah.
So that term which I'll get because of this factorial 5 and to the power 4, that will anyway divided by h, and hence
no. What I'm saying is that why will you divide with h? Won't you divide with h square, because you're trying to calculate dou square u by dou x square, right?
So then we have to go for at least 6 orders, right?
Isn't it? I mean, otherwise, because if you divide with h, you are only seeking dou u by dou x.
I'm sorry.
Correct. You can double check. Yeah, you can double check.
Yeah, fine, sir. But approach is okay, sir.
Approach is fine. Approach is same as what we have done. Yeah. Either
then
you can use this method.
We have to expand it till I plus 6, sir, if I'm not wrong.
Till 6, isn't it? Because 6 by 2 is what 6 minus 2 is what 4, right? So I think you probably have to go to till 6 maybe. I guess.
So I think we can expand up to 5, and order 6. We have to equate up to order 5 equal to 0. So.
Right. So 6 will anyway be order h power 4, so you don't need that value as such. Correct.
So we will have 5 by 5 matrix, right, sir?
You will have a 5 by 5 matrix, yes.
Noted, sir. Thank you.
Yeah, because you are anyway having 5 coefficients, no? Your stencil is I plus 1 and so on to I plus
It will
4.
come
I
I
think you
plus
have-
5. It will come
Correct,
I plus 5 also will come over here.
Yeah, right. Because it is from I to I plus 5, including I and I plus 5. That will be 6 points.
Yes, sir.
Yeah.
Okay. Thank you, sir. Thank you so much.
Okay, thank you. Yeah.
So just one request actually, like the
Yeah.
assignment submission date is given as 19th. We just had a exam like this last means yesterday, so we couldn't get
Sure.
much time actually. Like, would it be possible to change the date to Sunday, sir?
Sunday. Yeah, okay, sure. I'll inform the code office to change it to Sunday. Sunday
Yeah,
is what?
20
Sunday is 23rd. Okay, 23rd. Fine.
23rd.
Yeah.
Yes, sir.
I'll
Sure,
change
sir.
it.
That would be
But
very
it
helpful,
may
actually.
be, but it may be possible that I may post some assignment starting, end of the week or beginning next week, something like that. Okay. For the ODE.
Yeah, sure.
Okay, they'll have some overlap
Sure,
there.
sure.
Yeah. Okay.
Sure, sure,
I'll
sure, sure.
I'll extend it to
Thank you,
Sunday.
thank you,
Okay.
sir.
Thank you, sir.
Fine.
Thank you so much.
All right. Yeah. Okay. Thank you, everybody. Talk to you tomorrow at 4 o'clock. Okay. We will look at the so system of ODEs is done. We will look at the solving for the boundary value problems tomorrow. Okay. All right.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Bye.
Okay,
Thank
thank
you.
you, sir.
Yeah. Thank you.
Thank you so much, sir.
Thank you. Yeah.